All right, this is a video for section 4.5. We'll start with the warm-up, which is what can I figure out about a rational function from the equation. So let's pick just a rational function, f of x equals 3x minus 4 over x plus 1, x minus 2. All right, there's a lot you can figure out from a rational function. First thing you can figure out is where are the vertical asymptotes? And remember that a vertical asymptote means the outputs go to positive infinity or negative infinity. And another way to say that, or when you look at a rational function, your outputs are going to go to positive or negative infinity if this happens, if the denominator is 0. Because as you get closer and closer to 0 in denominator, you're dividing by something close to 0, so the output goes to something very, very big. So in this case, my vertical asymptotes are at x equals -1 and x equals +2. Because if I put -1 in here, this term equals 0. If I put +2 in here, that term equals 0. All right, you might want to ask, where are the x-intercepts? There might just be one. There might be more than one. And that is if the outputs equal 0, which you get if the numerator equals 0. And so in this case, you have one x-intercept and it's when x equals 4, because if x equals 4, then this top term is 0. You have 3 times 0 divided by some things. Anything times 0 is 0. Okay. Domain and range. All right, so you've got this rational function here, and you want the domain. For a rational function, the easiest thing to do is find the problem areas and exclude them. And you'll have problem areas when x equals -1 or x equals 2, because that would make the bottom 0 and you can't divide by 0. So as long as I exclude those two values, everything else is fine. So if I were to write this in an interval, I can start all the way back toward negative infinity. I can go all the way up to -1, but I can't include it. So I cut it out. That's what I think about when I see this term, is I'm cutting out the -1. And then I can go up to 2, and I cut out the 2, and then I can go all the way out towards infinity. Okay, as far as the range, well, for your warm-up, you have a graph. For this one, I'll just say you are going to get up towards positive infinity as you approach one of these numbers, either from the left or from the right. And you're going to get down to negative infinity as you approach one of these numbers from the other side. So in this case, you are going to be able to get to any real number as an output. So you should have a range of -infinity to infinity. And my disclaimer is I'm making these up off the top of my head, so I may sometimes make mistakes, and I hope I don't, but maybe I do. All right, that was part of our warm-up. Question 3 asks you to review some possibility or some possible interpretations of a rational function. I'm just going to use the same rational function. So I know that x equals -1 and x equals -2 are not in the domain because that would make the denominator 0. So I know there are vertical asymptotes at x equals -1 and x equals 2. I could write my domain by cutting out my two problem values of -1 and 2. And I can find the zeros by making the numerator equal to 0 when x equals 4. All right, moving right along to 4.5 workbook section. 4.5, yeah. I got a lot of papers. So, all right, let's do our summary. I think that's worth it. Have a summary before you go through it. X-intercepts, a summary of rational functions from equations. All right. 1, x-intercepts occur when the numerator is 0. So look for the factors in the numerator. 2, vertical asymptotes occur when the denominator is 0. So look for the factors in the denominator. And the domain is everything except the vertical asymptotes. That's where I would start with my summary. Moving right along. 4.5, question 1. You've got a polynomial that is written as one polynomial over another and also written as a factored polynomial. I don't want to have to do that math, so I'm only going to write it as factored. And again, I'm using different terms, so you get more practice. So there's my polynomial, x minus 5 times x plus 2 divided by x minus 3 times x plus 4. And I'm happy to go backwards at this point. That's x squared minus 5 plus 2 minus 3x minus 10, and x squared minus plus x minus 12. So if I wanted to write it multiplied out, that's what I should get. All right, so where that is the x values is p undefined. The answer is at the vertical asymptotes. And that's going to occur at x equals 3 and x equals minus 4 because the denominator is 0. So the domain, I just have to cut out those numbers. So I can start all the way back at -infinity. I can go all the way up to minus 4, but I have to cut it out. Then I can go up to 3, but I have to cut it out. And then I can go all the way up towards infinity. And that's my domain. The equations of the vertical asymptotes are right here. The vertical asymptotes are your problem spots. And that's how the vertical asymptotes are connected to the domain of a rational function. Let's just get a little more practice and find the zeros. The zeros are x equals 5 and x equals 2. -2. X equals -2. Because that's where the numerator is 0. All right. Moving right along. 4.5, question 3. So now we're getting into end behavior. Okay, when we talk about zeros, here's an aside. Zeros and vertical asymptotes are, I'll call it interior behavior or middle behavior. Generally, we think about those numbers are kind of small. End behavior is when x goes to infinity or x goes to negative infinity. So again, here's where you cover up the middle section. It doesn't matter what's going on in the middle, you cover all that up and you look at what's happening at the end. Recall from polynomials, so here's another an aside kind of. Recall in polynomials, use only the leading term to determine end behavior. So for example, if I have p of x equals 3x squared minus 2x plus 8, for the end behavior, I can ignore all that. Or here's another one, if q of x equals minus 5x to the fourth plus 3x cubed minus 7, I can ignore all of that for end behavior. And that one behaves like a positive quadratic, and that one behaves like a negative quadratic. Well, it's the same way with rational functions. Let's take my rational function, and I'm going to write it as 3x squared minus 2x plus 8 over minus 5x to the fourth plus 3x cubed minus 7. You may have noticed that those are these two polynomials. For end behavior, ignore everything but the leading terms. All of this stuff changes zeros and vertical asymptotes, but it has no effect on horizontal asymptotes or end behaviors. So as I get big, my rational function basically looks like 3x squared over minus 5x to the fourth, which I could actually simplify now. Messed that up. I can simplify as 3 over minus 5x squared. Oh, and we know what that function looks like because we know the parent function looks like 1 over x squared. So the end behavior of r of x is going to be the same as the end behavior of 1 over x squared. In particular, as x goes to infinity, r of x is going to go to 0. As x goes to minus infinity, r of x is going to go to 0. Just like 1 over x squared. Let's do another one. Here's a 4.5. Use 3, 4, and 5. Okay, let's take a rational function f of x, and let's look at 5x cubed minus 6x plus 4 divided by 2x cubed plus 8x minus 3. There might be some vertical asymptotes, there might be some zeros, but I don't know because it's not written as a factored polynomial. So I'm not going to care about that. If I want to know the end behavior, and I recommend you actually do this, if you're asked on a quiz to find the end behavior, remind yourself what you're doing by scratching that out. That looks a lot like 5x cubed over 2x cubed, which is just 5 over 2. What does this mean? This means as x gets very large, f of x approaches 5/2. And that right there is the definition of a horizontal asymptote. So our function f of x has a horizontal asymptote at y equals 5/2. We can also say as x goes to infinity, f of x goes to 5/2, and as x goes to minus infinity, f of x goes to 5/2. So if I were to sketch this, I might pick my point 5/2 and put a horizontal asymptote in there. I don't know exactly what's happening, but I do know at the end, probably looking something like this. Maybe it's like this with, I don't know, there could be an asymptote in here, it could go around, maybe like that. I don't know, but I do know as I go out towards positive infinity, it goes to 5/2. As I go to negative infinity, it goes to 5/2. Let's do one more, because there's another possibility. 4.5 q's 3, 4, and 5. Let's look at our functions. Going to be 6x to the 4th minus 2x. Let's keep it simple. And 3x squared plus 4. All right, so for my end behavior, I'm going to scratch out all those extra terms. And I'm going to realize it looks kind of like 6x to the 4th over 3x squared, which I can simplify to be 6/3, which is 2, x squared over, or x to the 4th over x squared is x squared. So I don't know exactly what my function looks like, but I do know once it gets through with all that interior behavior, there's an asymptote here, it's going to end up looking like 2x squared as I get way out towards infinity. So in summary, for end behavior, look at the leading terms of the numerator and denominator. Ignore the rest. Simplify the fraction compared to maybe a parent function or a power function. Parent function might be something like y equals x, or y equals x squared, or y equals x cubed, or 1/x, or 1/x squared. Power functions, it could be something like x to the 7th, could have like a -2 there. It could be like a 3x to the 4th. You could have something like -3 over x to the 5th. But you're going to end up with something where there's only an x term in the numerator, or only an x term in the denominator, or maybe no x term at all, 3/2, or y equals -7, or something like that. All right. So let's put it all together. I'm going to jump ahead to question 11, because we covered a lot of the concepts that get us up to question 11. And let's look at some kind of rational function. We'll make it simple like they do in the workbook. X minus 3 over x plus 5. So start with vertical asymptotes. That's where the denominator would be 0. So x equals -5. So my domain is everything except those problem areas. So I'll have to cut out the -5. My x-intercepts are where the numerator is 0. If you want to know the y-intercept, just plug 0 in. Usually we can figure that out pretty easily from a rational function. End behavior. I'm going to rewrite it because I used this whole thing for my interior, so I don't want to get rid of it up there, but I will write it here. Now I'll scratch out all this other stuff. That basically looks like x over x, which is just 1. So as x goes to infinity, f of x goes to 1. And as x goes to minus infinity, f of x goes to 1. And so I have a horizontal asymptote at y equals 1. And I believe that's all we really care about. Range is trickier on rational functions without a graph, so I'm not going to do it for this one. Okay, end of video.